Hi, everyone. Thank you for coming. Thank you for inviting me. Pretty nice. Okay, so I guess Paul has done the hard work here. It's part of my PhD work. So as you imagine, there are quite a few people involved. I would like to acknowledge my supervisors, co-authors, and all the technical staff I've worked with, and as well as those institutions. Carbonate concretion, a window into the past. I'm going to give you an overview of carbonate concretion and then present a couple of case studies. One about paleo-environmental recorder. Can we record paleo-environmentals with carbonate concretion? And do carbonate concretion also preserve some paleobiological signal? And finally, I'm going to try to open up and discuss a bit with you about future work and future direction for the research on carbonate concretion. So let's get started. What is a carbonate concretion? Well, to put it simply, a carbonate concretion is a patch of cemented sediment within a less cemented host rock. Carbonate minerals involved, well, calcite, siderite, and dolomite are the most common one, either one or the other or a combination. They occur throughout geological time since the Proterozoic, although they are more common since the Phanerozoic. You find them in black shale or in sandstone. That's where you find them most commonly, really. They're also a tourist attraction. So here is a special place in Kazakhstan where you have like from very small to very big concretions. I thought those photos were quite impressive, but you can find them a bit closer as well in New Zealand on the east coast of the South Island. That's not me, but I have one a bit similar. Anyway, so concretion are also very interesting for collectors and people who are into fossils, museums as well, because they preserve exceptional fossils, really. You have a really high level of detail. So here are a few examples. Here is the myriapod from the Carboniferous, and unfortunately we can't see here, but you actually could see on the photo the little legs of the giant bug. It was quite high level of detail. Here is a baby crocodile from the Jurassic, about 20 centimeters long. And those two are some Australian carbonate concretion from the Gogo Formation in northern WA. So those are gogo fish from the Devonian. How do you get a carbonate concretion? So that's what I'm going to try to explain quite simply. Based on that paper, so how to form a carbonate concretion with a pyrite rim around at the outer edge of the concretion. So for that, you need a stratified water column, which means like you're in the ocean, you have an oxygenated top layer of the water column where you have little organisms living, and an anoxic bottom layer of the water column with anoxic sediment, potentially rich in hydrogen sulfide. So that's our setting. What's going to happen? Well, we also need something, and that's Nemo in this story. We need a center of organic matter decay to form the concretion. So here, unfortunately, we have to kill off Nemo. We will sink onto the ocean, get into the sediment accumulation and get buried. There in the anoxic sediments, you have an enhanced microbial activity dominated by sulfate reductors, methanogens, and anoxic methane oxidizers, but also some iron reductors, some manganese reductors, and quite a few others have been mentioned throughout the literature, because you can find hundreds of papers on carbonate concretion, hundreds. Like really. So here we have our decaying organic matter, poor thing. These processes lead to the formation of byproducts, and those byproducts, carbonate and H2S, diffuse relatively outward from the decaying carcass to the outside, to the sediments. Relatively, there is an inward diffusion of ions, so iron and calcium, from the outer sediment towards the carcass. And that leads to the precipitation of calcite, which is here represented in light color. That's not me shaking. And pyrite rim around, which is the darker gray color. Is it shaking? Okay. Sorry. Okay, so a big question was, what is the timing of carbonate concretion formation? Well, that's not really a new question. There have been studies on that since the 60s. And quite a few people suggest that it's actually quite long to form, thousands to millions of years, while others suggest, well, it's only taking weeks to months. In the case of fossil, what is important is the timing of the onset of the concretion growth, which will isolate the decaying organic matter, which will isolate the dead organism from its surrounding environment. So that's when we link it to our case study. Carbonate concretions. I'm going to present 3 carbonate concretions from the lower Jurassic of southwest Germany. So, more precisely, they are coming from the Toarcian, 183 million years. It's a known mass extinction, not one of the big 5, but quite significant. It's linked to an intense volcanism, a greenhouse effect, and, well, consequently, global warming. There is marine transgression associated with it, and an ocean acidification. Okay, so that's just to put the context. There is also water stratification, very useful for carbonate concretion. All right, so that's Jurassic, lower Jurassic at the Toarcian. So you have 2 major continental landmass, 2 big oceans, one on the outside here, and the Tethys Ocean. And Germany is about there. So it's in shallow marine environments with deeper subbasins. Well, again, stratified water column, that's a very important keyword here. And important accumulation of organic matter in the sediments. And actually during the Jurassic, during this time of the Jurassic, there is a very important petroleum source rock depositing in Europe. One of the most important that people are looking at when they go in the North Sea. Well, anyway. So what do the 3 carbonate concretion I'm presenting here have in common? They have a preserved nucleus. So earlier it was the Nemo fish. In the concretion with the fossil, it was the myriapods, the crocodile. Here's this little blob. We have the presence of an enriched pyrite rim and of sedimentary bedding. So I'm going to refer to them as concretion rim or pyrite rim, concretion body, and nucleus. And here are the 3 concretions. So I'm going to try, like the objective of my studies were to figure out carbonate concretion. Do they hold some paleoenvironmental information? What clues do they contain for the processes of formations? And what paleobiological information do they contain? Well, given that they have fossils in them, we were quite hopeful. The first case study, I'm using mineral characterization, bulk geochemistry, and biomarker and compound-specific stable isotope geochemistry. Don't worry about that just now. We'll start with the easy ones. Here are the 2 concretions. We also compare them to the host shale, so the surrounding sediment was also analyzed. And those 2 concretions, what do they have in common? They have a jet nucleus. So here I'm going a bit out of the topic. What is jet? So jet is derived from decaying woods. It's composed mainly of carbon. It's a mineraloid rather than a mineral, and it's used to make jewelry. Well, it's actually used for a very long time. They even found some little figurines over 10,000 years old made in jet. Became famous during the Queen Victoria reign, because after she lost her husband, she actually put the jet as part of the official mourning dress. Let's go back to our topic. So that's the surrounding shale, the Posidonia shale mineralogy. What do we see? We have dominance of calcite, quartz, pyrite in yellow here, and some phyllosilicates, mainly clays, muscovites, little things like that. That's the concretion rim. So we see strong dominance of calcite, pyrite, and quartz, although here it seems like the pyrite is very underrepresented here. Concretion body, we have only a calcite signal. Oh, those are XRD. Those are diffractograms, by the way, sorry. But here you see that you still have quite a bit of pyrite, which is the white in those pictures. The gray is the calcite. So you still have quite a bit of pyrite, a few quartz grain, which is the dark darker gray there. What can we say about that? Well, okay, the mineralogy of the host sediment is not preserved in the carbonate concretion. It's been overprinted by the concretion growth processes. So next step, we look at the stable carbon isotope of the carbonates. And what does it tell us? It tells us that it gives us an information on the source of the carbon that is used in making the carbonates. So let's look at it. While the host sediment has a value of minus 1.8 per mil, which is very typical marine carbonate value, the concretion body, so the inner parts here and here of the concretion have a value of minus 15 per mil, and the concretion rim is slightly more enriched with a value between minus 10 and minus 8 per mil. What does it mean? Well, it means that, again, the carbonates source is different in the concretion is different from the one in the host sediments. What else does it mean? To have values that negative, you need to be in this area of this diagram. So it's like sulfate reduction. Well, we know actually in that case it's dominantly sulfate reduction. So what it means is the sulfate-reducing bacteria have a major role in the formation of carbonate concretion. That was also suggested before, but we confirm it in our concretions. And yeah, that's about it. I know that the pyrite rim that we've seen on the outer part, which is slightly more enriched than the concretion body, the pyrite rim might not have the same contribution from sulfate reducer. Maybe some other organisms are involved, likely iron reducers in that case. Okay, so now we talk about bulk organic matter. What do we have? We looked at the total organic compound and the hydrogen index. The hydrogen index is commonly used to evaluate the state of preservation of the organic matter. The higher the HI is, the better preserved the organic matter is. So what do we see here? Well, there is a drop. It's quite constant and quite high in the concretion, but there is a drop in the rim. And here it's a bit more progressive, but also. So what does it mean? It means that the organic matter in the rim is not as well preserved as it is in the body. So likely, whatever happens, whatever microbial community occurs in the outer rim is present and is active in the outer rim, degrades more efficiently the organic matter or takes more time to form or something like that. So far, everything represents the processes of concretion growth. All the parameters, the bulk parameter we've looked at, well, we don't see much signal from the host sediment. We don't know much about the paleo environment, more about the concretion growth processes. So that's why I jump into biomarker. So let's go back to basics. Biomarker, well, not yet. You know fossils, how do they form? You have this organism. When they die, if we are lucky and the right environmental condition of preservation, you get some beautiful fossil trace or soft tissue and hard tissue. So you get the skeleton, the shell of a clam or something like that. Well, and it looks a lot like the original organism. Well, for biomolecules and biomarkers, it's the same principle really. It's like you have this quite complex organic molecule, so biological molecule with some OH groups, but a very simple or very distinct shape. And if you're lucky, and those get preserved, you get an hydrocarbon skeleton. So you lose your hydroxyl groups, but you preserve the skeleton of the molecule. And that can tell you information. For example, here, that is formed by bacteria. And the skeleton here tells us, well, okay, that belongs to this one. That means there were bacteria involved, if you find that. So that's what it looks like when you actually look like it. You have a lot of compound, and each compound corresponds to a peak. Don't worry about anything else than that. That's just to illustrate. So what we had is biomarker distribution in the rim, in the concretion body, and in the shale were similar. And they were all representing a marine signal. We took it a step further, and we looked at the stable isotope ratio of those individual peaks. So don't worry about it much more. But here in black is the shale, and down is the concretion sample. So what we know is, although the distribution of the biomarker is inherited from the shale, somehow there has been a tiny bit of overprinting on their stable isotope composition. So biomarker distribution can give us information on the environment, yet their biomarkers seem to have had some kind of overprinting on them. What we can say about this first case study, well, carbonate concretion can give us insight on the processes of formation and the microbial communities involved. But they can also give us insight on the paleo environment at the time of deposition of the host sediments thanks to the biomarkers. Okay, so now second case study. Sorry, I usually have water. All right, so here another concretion, the third one. We've done some microcharacterization, elemental mapping, and again, biomarker and compound specific. Stable isotopes. So what is different in this concretion? Well, first, it was whole. And, well, oh yeah, what I'm putting there are always like nicely polished slice in the middle of them. And you have quite a few bones, and what is important is this vertebra here. Those bones belong to an ichthyosaur. So what are ichthyosaurs? They are those little dolphin-looking marine reptiles from the Jurassic. They appeared in the Triassic. They are fast swimmers, and they eat cephalopods and fish. They really are very much like dolphins, except they are not mammals, but reptiles. So let's go back to our conclusion, a bit bigger. First off, we looked at the elemental distribution of the phosphorus, because we know that bones, if they are well preserved, they will still have some phosphorus and some kind of apatitic or fluoroapatitic mineralogy. And here we see that the phosphorus in pink is very well associated with the bone. When we look at the, where is it? Okay, here. The inner part of the bone, the porous bone or trabecular bone, and we looked at it using just optical microscopy, we see that there's a very abundant porosity, estimated at about 60% using point counting, which fits with what was previously reported for ichthyosaur vertebra bone. This porosity was then filled by cement. So here you have some calcite with spar calcite, and here you also have some cement in barite, which is the very colorful one. So okay, that's quite nice. What else? Well, a bit further, we looked at a thin section using SEM, and we found that a bone osteon. So osteons are characteristic of mature bone remodeling and renewal. So basically, if you break something, or when your bone needs to mineralize and stuff, they repair, they create those kind of little structures. It has preserved the aversion canal, which is here. It surrounds blood vessels and nerve cells, the lamellae, and the osteocytes. The osteocytes have a role in the synthesis of bone collagen. So I'm just putting that out there. Okay, now look at the biomarker. And actually here, we don't want to look at these molecules so much as those ones. Those highly functionalized lipids, those biolipids that we all create. So here is a bacterial one, but I thought possibly we could put something we all know. Cholesterol. So we all produce cholesterol. We've all heard about you have to be careful about your cholesterol level. Well, that's a biolipid. And in the geological record, we would expect that, a geolipid. So what's the difference between those two? They look very much the same, but the geolipid has lost the hydroxyl group and the double bonds. Okay, so now transition. Biological molecules are very rare in the geological and in the fossil record in general. Yet, in 2013, another PhD from Curtin University studied this carbonate concretion. So it doesn't look like much, but this white stuff here is actually a fossil. Biomarkers have shown that this fossil was a crustacean, so that's to tell you how powerful biomarkers are, because making that out of this is not easy. And in that concretion, in the fossil layer, what did Ines Melendez found? She found the association of sterols, so the biomolecules, the cholesterol, together with the most diagenetically, the most mature molecule of the streets, like the most mature steroids, together in a single sample, which was very, very unique and very special. And what I forgot to mention is that this concretion is actually from the Gogo Formation, so 380 million years old. So basically, she reported a continuum of steroids, but also the oldest steroids ever reported. She put the oldest steroid back a bit more than 200 million years. So that was quite a find. I thought, oh, my concretions are way younger than that, so let's have a look. And we did find the association of geomolecules with biomolecules. And actually, that was how they looked. Very high in the bone and much lower in the rest. Actually, they were so high in the bone that you could do some stable isotope on the single molecule. So we have the stable isotope composition of the of the cholesterol in purple, and of, well, the ethyl cholesterol, another sterol, in green. And we see that there is a major shift between the two. This shift is attributed to the difference in origin. While the cholesterol in the bone comes from the ichthyosaur and its diet, reflects its diet, the other sterol is attributed to the primary producers of the ancient water column. So that was quite a find. That's still the second oldest sterol. So very exciting for PhD students, yay! But, well, what else could we find? Well, I kind of broke a tiny piece of the porous bone and had a look at it using the SEM. It looked like that. Oh, well, you have some very smooth surfaces, which are the calcites, the cement filling the porosity. And I thought, well, if people suggesting that carbonate concretion containing fossil formed very early, this calcite is probably there for about 183 million years and might have trapped something underneath, like something that has never seen the day since then, like it's been preserved from everything. So let's play around, a bit of acetic acid, remove the carbonate. As you see, I wasn't very patient, but I removed enough to have nice surfaces to look at. And that's the kind of fibers I found on the bone. So I was like, ooh, could that be collagen fibers? And that's when my supervisor, Clitic Rice, was like, yes, well, you have to compare that to a modern reptile bone. So she ordered, the little story is, she ordered some crocodile legs. She went to a butcher to have him cut out the flesh, cut the bone in tiny pieces. Apparently the crocodile's bones are very hard. And she gave me some almost defleshed pieces of crocodile legs for me to play with. So I tried a few methods. I've read a bit, of course, and put a piece in the oven. I put a piece in bleach. I put another piece in hydrogen peroxide, made some combination of all those to try to reveal the collagen fibers, because I wanted to remove the organic matter and the proteins, but I didn't want to remove the collagen. So there was a bit of trial and error, but at the end I got that. So I don't know for you guys, but for us we were quite convinced. We had the oldest collagen fibers associated with the bone. Unfortunately, by the time we managed to publish it, there was a second oldest. Okay, what else did we have? We had those little structures. So, well, I got very excited when I got that. And I was like, oh, could they be organic in origin? So let's play around with the SEM, do some EDS analysis. And what we found is that when you pointed the EDS at these structures, you had a very high carbon peak, much higher, or quite higher than the oxygen peak systematically, and a very high count. When you pointed out, so in those ones, for example, which is outside next to it, you got much lower carbon peaks and systematically lower than the oxygen. So that I was getting very exciting. And I thought, well, let's go a step further. So we went to the fifth SEM, and we cut a slice across those cells here. Then we took that slice and put it into the TM for elemental mapping. So that's a photo of this little one here. And what we saw is that the carbon was exclusively associated with this structure. The oxygen was present in both, and the sulfur was dominantly associated with it. So yes, those structures have preserved an organic signature. Those structures are organic in nature. So now I can say what I thought they were. I was like, ooh, very excited. That looks like this kind of structures. Those look like red blood cells to me. Okay, I'm not a nematologist, but, well, doing a bit of Googling. And one day we even found those in association with one of those cells. And when you do Wikipedia blood cell, that's the kind of figure you get. To me, I was like, oh, wow, that's amazing. That looks like this one. This one, the platelet, looks like that one. And this is this one, a white blood cell. Yet, those blood cells in the ichthyosaurs are way smaller than human blood cells. So that's, okay, up to here is what we've published. And now that's me suggesting. All right, so let's find something about blood cells. I found this old paper, quite old, 1875. This guy made actually a very thorough comparison of blood cells in different vertebrates. And what he found is, okay, mammals have the smallest red blood cells with a great variety of shape and size. They don't have a nucleus. They are anucleated. While all the other ones are bigger, well, even very big, and have a nucleus. So that's the size of our blood cells. It should be in those reptilia stuff. Yet, it looks much more like it belongs here. So that was quite a problem. Anucleated red blood cell facts. Well, first idea, all mammals have anucleated red blood cells. That's one of the things people told us. Well, that's actually wrong. Some mammals, camels family, have a recognizable amount of nucleated red blood cells. Okay, that was enough for me. I was like, yes, what else? Okay, well, okay. But then non-nucleated red blood cells only exist in mammals, even though they don't all have that. Well, that's wrong again. And those guys here, the salamanders, and I don't know how to pronounce that. This little nasty fish with a lot of teeth here, well, those one have up to 98% anucleated red blood cells. This one, 1 to 3. Those guys, 0.5, but it's still something. And this little fish here was reported in that paper from 56 to have 100% of anucleated red blood cells. So no, not only mammals have anucleated red blood cells. So that was, okay, that's for the discussion. Now let's go back to the ichthyosaur. A bit of context. Okay, they appeared in the Triassic. The Triassic is shortly after the Permian Triassic extinction events, with very low level of oxygen, well, compared to today anyway. Today is 21%. So the Permian Triassic crisis is here, 252 million years. It's called the Great Dying. Like 95% of the marine life was extinct, 70% of the terrestrial life. It's the biggest mass extinction on our planet. It's marked with very active volcanism, methane release, increased CO2, decrease of oxygen, marine transgression, inhibition of marine circulation, so that means, again, water column stratification, high level of hydrogen sulfide in the oceans. Okay, so all these conditions were quite interesting when you consider that these little ones were swimming as fast as 40 kilometers per hour, so they needed a very efficient oxygen transport in their blood. Well, yeah, but you have a low level of oxygen. Oh, how to adapt to that? And that's our hypothesis in the paper. That's not me. That's a real one. And we think that the ichthyosaur evolved smaller red blood cells that would be more efficient for oxygen transport. I'm not talking about anucleated here, just to be clear, but I'm talking about it here. Well, could the ichthyosaur have also developed anucleated red blood cells before the mammals? And, well, the mammals did that to have more space to transport hemoglobin in their red blood cells and have smaller cells. So it's all about efficiency. Could those guys, who have no representatives at all today, have evolved the same type of blood system, oxygen transport? And then it would be convergent evolution. I can't answer that. I guess to answer that, it's part of the future work slide. It would be part of this one here. To try to answer that, we would need to look at much more samples containing vertebra bones, containing bones from the Jurassic, from Ichthyosaur, from dinosaur, very well preserved things. The problem with that is most people don't. You find a beautiful fossil, you don't want to crush it and attack it with acid and cut it in small slices and extract the biomarkers. It's all destructive, so you don't want to do that, and not that many people actually looking. Nobody actually at the moment much is looking at that. Except maybe at the GSA where my supervisor is following work on carbonate concretion, and currently has a honor student medicine trip working on biomarker in siderite concretion, which, well, it's not a bone, it's a leaf, but still it's something, destroying fossils. We're in the process. We could also investigate a whole range of carbonate concretion from different ages, environment, mineralogy. That's been done a little bit, but most of the time people are separating the different disciplines, so a bit of inorganic geochemistry, a bit of organic geochemistry, mineralogy, imaging, but it's hard to get people to combine and to actually discuss about what those different approaches give to the story. So I've done this one, that one, that one. Yeah, okay. The last bit here is something I haven't mentioned too much in these talks, but seems like carbonate concretion are really good at preserving fossils and also molecules. So they could have a role to play in the understanding of the early life on Earth. Most of the very ancient things are, as you say, as inorganic geochemistry cooked. You can't really get much information from the organic aspect. Yet, if carbonate concretion are able to preserve biomolecules over 380 million years, potentially there is something to do for even older things, maybe not biomolecules, but maybe something. So I think there is a role, they have a role to play in early life studies, and as carbonate concretion are formed by microbial communities, well, they could also play a role in astrobiology. When you look at the nice rover photos of the Mars sediments, what if you found there a big carbonate concretion? What would that mean? To date, I think people are all agreeing on the role of microorganisms, in their formation. So potentially that would be a very good clue for extraterrestrial life at some point. Maybe not now, but maybe in the past of the Martian history. Okay, I want to thank the sources of funding, CSIRO, where I am at now. And thank you all for coming with this weather and for your attention. Thank you.